Okay, and we're all over the map. So how do you actually answer a question like this? Well, as I said, taking a guess or just kind of thinking about it without actually writing anything down probably isn't going to work. So let's see if we can reason this out using these two fundamental rules that we have. So I have circuit number 1 has some EMF value, and we have a wire connected to it, and I'll kind of draw it so we show some thickness in the wire. This wire has a length L, has a cross-sectional area A, and it's somehow a nichrome. Now, we don't know, haven't told you anything about what the material properties of nichrome are, but we do know that the second circuit has a wire that's made out of the same material. So that means what's the same? The mobility and current, well, we'll find out, but in terms of just material properties, the N, which is, what's N? Number of electrons per unit volume, right? So we know that's the same for both. Well, and we also said that it's the same battery, or the same type of battery, so we'll say it's the same EMF in both. So what do we know? Well, we know, let's apply the loop rule. Loop rule says that we go round trip, and the potential difference has got to be equal to 0. So we know, well, that the electric field, actually by the node rule, we know that the electric field everywhere in a uniform thickness wire should be the same. Okay, so that's just going to be E1. And that's positive, that's negative, right? So if I apply the loop rule here, let's say I start at the positive terminal, go around in the direction of the electric field, and then go through the battery, and go back to where I started from. Go around in this direction, I'm going in the direction of the electric field, so the potential difference should be negative, okay? And so the magnitude is going to be, so we have a negative, and it's going to be what? What am I going to get for the magnitude of the magnitude of the potential difference in terms of the electric field and the length? EL, okay, minus E1 times L, fine. And then I'm back to the negative terminal, the battery, and so when I go across here, I get a positive or negative potential difference. I'm going to go positive. I'm going from the negative to the positive. I'm going against the direction of the electric field inside the battery, which may be, it's going to be different than E1. But that potential difference in an ideal battery has got to be numerically equal to the EMF. So I say plus EMF equal to 0. I know that E1 then is equal to EMF over L. Okay? Well, if I do the same thing here, I have E2 pointing in that direction, right? And now the length is 3L. So if I go through, find the potential difference going from the positive to negative, it's going to be what? So I'm starting here, I'm going around in that direction, going along the direction of the electric field, and so I get for the potential difference, what? E times 3L, right? E times 3L. It's going to be negative E3L. That's this, we're calling this E2, okay? And then I go across the battery and I get another contribution of the EMF, right? Let's then set it equal to 0. So E2 is equal to what? EMF over 3L. So how does it compare to the electric field in the first circuit? It's 3 times smaller. E2 is equal to 1/3 of E1. So the correct answer, well, they're putting E1 on the other side of the equation. So the correct answer is 2. E1 is equal to 3 times E2. Okay? So get all else being equal, same battery, same thickness, you have just a single type of material, all you're doing is changing the length, then the electric field goes down, right? The electric field changes from, we're comparing two different electric fields in two different circuits. This isn't a sort of a node rule situation where we're looking at the relating two currents in the same circuit. So the electric field depends on the length, right? So the field is going to go down.